If every stock in the entire global market, thousands of them, could be described by just a handful of numbers, what would those numbers be? 3 episodes ago, in Ep13, we drew a hyperbola, a simple, beautiful curve, risk on one axis, expected return on the other, the boundary called the efficient frontier. But that picture was only two-dimensional. Today, we leave that flat plane behind and step into something far larger. We step into the factor universe. Recall the picture. 3 assets, a stock, a bond, an alternative. Combine them with weights that sum to 1, and a whole cloud of possibilities opens up. The upper edge of that cloud is the efficient frontier. 2 dimensions, 1 curve, clean and complete. And yet behind those 2 simple numbers hides a structure with not 2, but many, many dimensions. Ep03 left us with 1 curve. Today we add a single dot, the market. And the moment that dot exists, every line of equilibrium must pass through it. Here is the first surprise. There is not 1 such line. There are 2. On the left, the capital market line. The horizontal axis is sigma, the full risk of a portfolio. The vertical axis is expected return. The line passes through the risk-free rate at sigma equals 0 and rises with slope equal to the Sharpe ratio of the market. Every efficient portfolio sits exactly on this line. On the right, the security market line. The vertical axis is the same, expected return. But the horizontal axis is no longer sigma, it is beta. The intercept is again the risk-free rate. The slope is the market risk premium. And on this line, every single asset, efficient or not, lies exactly here. So what is beta geometrically? Pick any asset, call it asset 1. Plot its return on the vertical axis and the market return on the horizontal. Draw a cloud of joint outcomes. Fit a line through the cloud by least squares. The slope of that line is beta. For asset 1 in our universe, beta is 1.10, and the line passes through the joint mean. N risky assets entered this episode. Each had its own variance, and its own covariances with n-1 others, a whole matrix of relationships. Then we introduced the market. 1 fixed reference. Suddenly, the entire matrix collapses into a single column of covariances with one thing. That column, divided by the market's variance, is the only number that matters for pricing. Beta, the price of correlation with everything. There's a problem with the picture from the last section. CAPM says one number, beta, explains every asset's expected return. Empirically, it does not. For decades, 2 patterns kept showing up. Small cap stocks earned more than their beta predicted. Value stocks earned more than their beta predicted. 2 clear, persistent anomalies. In 1992, Eugene Fama and Kenneth French published their answer. Beta is not the only dimension that matters. Take any single stock. Its excess return above the risk-free rate, decomposes like this. First, exposure to the market. The classic CAPM piece. A loading of 1.05 times a market premium of 7%, 7.35. Next, the size factor, small minus big. A loading of 0.4 times 2%, 0.8. Next, the value factor, high book to market minus low, 0.55 times 3.5, nearly 2. Add an alpha, the part the model cannot explain, and a residual, noise around 0, total, 11%. CAPM alone predicted 7. The other 4% lived in dimensions CAPM never asked about. Picture the universe of stock portfolios in 3 dimensions: horizontal, market beta; depth, size loading, how much it moves like a small cap; vertical, value loading, how much it moves like a value stock. 6 portfolios, sorted first by size, then by book to market. Watch them spread across the cube. Small value sits in one corner, big growth across from it. Each axis is a separate, persistent source of return. The factor universe is no longer a line. It is, at minimum, 3-dimensional. Where do these factors come from? They come from the data. Fama and French built them with a recipe, a 2x3 sort. At the end of June every year, take every stock and split it by market capitalization at the NYSE median. Small on one side, big on the other. Then cut each group by book to market. Bottom 30, middle 40, top 30. 6 portfolios fall out of the grid. Now the factors. Small minus big is the average of the 3 small portfolios minus the average of the 3 big. High minus low is the average of the 2 high book-to-market portfolios minus the average of the two low. Two simple averages of differences. And from these two numbers, an entire empirical literature grew. The Markowitz machine is mathematically beautiful, but it has one fatal weakness: its inputs. Plug in slightly different expected returns, and the optimal portfolio swings wildly between extremes. Estimation error gets amplified into nonsense. Garbage in, optimized garbage out. In 1990, two people at Goldman Sachs, Fisher Black and Robert Litterman, proposed an elegant fix. Don't ask the impossible question. Don't ask, what is the true expected return of every single asset? Start instead with the market itself. The market portfolio implies a set of equilibrium returns. Call them pi. Take that as your prior belief. The model the market itself is implicitly running. Then add your views, but only where you actually have an opinion. Asset 1 will outperform asset 2 by 3%, say. Then run Bayes. Geometrically, the prior is an ellipse, wide, centered on pi. Your view is a constraint along one direction in return space. The posterior is the Bayesian intersection, a new ellipse, tighter and shifted toward the view. Where you have no opinion, nothing changes. Where you do, the data and the prior compromise. That is the Black-Litterman model, a simple Bayesian update, and Markowitz becomes usable in practice. A classic balanced portfolio, 60% stocks, 40% bonds. Sounds balanced by capital. But what about risk? For our universe, 60-40 puts roughly 77% of total risk in the stock alone. The bond contributes less than a quarter. Equal capital, wildly unequal risk. Risk parity asks a different question, not, how do I split my money equally, but how do I split my risk equally? Solve for weight so that every asset contributes the same risk. For our three-asset universe with equal correlation, the answer is closed form. Weights inversely proportional to volatility. Asset 1, 31%. Asset 2, 23%. Asset 3, 46%. Each contributes exactly 1/3 of the total portfolio risk. This was the philosophy behind Bridgewater Associates' all-weather strategy. There is one more way to look at the covariance matrix. Diagonalize it. Sigma equals Q, lambda, Q transpose. The columns of Q are orthogonal directions in asset space, the principal components. The diagonal of lambda is the variance along each direction. For our three-asset sigma, the largest eigenvalue captures 62% of the total variance. Its eigenvector points in roughly the same direction across all three assets. That direction is the market itself. The remaining components describe the orthogonal residuals, how each asset deviates from the market. And here is the deeper point. A covariance matrix on n assets has n times n plus 1/2 unique entries. For 100 assets, that is over 5,000 parameters to estimate from limited data. The same eigendecomposition, applied to a covariance matrix of pixel intensities, gives you the principal components of an image dataset, the same math. There is one fact left to show you. It is the deepest result of this episode, and possibly the deepest in the entire field. We have built our portfolio theory around this. Minimize W transpose sigma W minus gamma mu transpose W. A quadratic objective with a positive semi-definite matrix, a linear term, one equality constraint. Hold this equation in your mind for a moment. Now look at this. This is the dual problem of a support vector machine, the algorithm that, for 2 decades, defined what a classifier was in machine learning. Minimize 1/2 alpha transpose K circle YY transpose alpha minus 1 transpose alpha. Same skeleton, different letters. Replace sigma with the kernel matrix. Replace the weights W with the dual variables alpha. Replace minus mu with minus the vector of ones. The Markowitz problem and the SVM dual are the same equation, written in different worlds. The efficient frontier of finance and the separating hyperplane of machine learning are two faces of one mathematical structure. And it does not stop there. Ridge regression, minimize the squared error plus lambda squared norm, expand it, and you get a quadratic in W with a PSD matrix and a linear term. Same equation again. Timeline, 1952, Markowitz. 1963, Tikhonov regularization. 1992, the support vector machine. Today, every neural network with weight decay. The portfolio optimization that built modern finance is the parent of every regularized model in machine learning. Same math, different world. Throughout this episode, we measured risk with one number, the standard deviation. It sits at the heart of every formula we've written. Markowitz, the Sharpe ratio, the CAPM, all of it. But variance only captures the average size of a deviation. And the truly dangerous events in finance are not average. Here is the bell curve we have been assuming. And here is the same distribution with fat tails, the student T with 3 degrees of freedom. At 3 standard deviations, the fat-tailed model says crashes are 5 times more likely. At 5 standard deviations, thousands of times more likely. What looks impossible under the bell curve is ordinary in real markets. That gap is the world of tail risk. Next time, in episode 14, we descend into the tail, value at risk, expected shortfall, and the geometry of disaster.